This is the discussion for chapter 2. It's going to be about data visualization. This is one of my favorite topics. We discuss it really early on for a very important reason. It is one of the first things that you should do. As Harry Potter fans, if there's any in this class, Severus Snape said, always. You want to always plot your data first. You do not want to dive into summary statistics or hypothesis tests. You want to always understand what your data look like first. You might be wondering why that's so important. Well, first, outliers and impossible values are really hard to find when we're just running a model or we're looking at a mean or median. They hide really easily. The second thing is it's going to help us understand what statistical approach we should use. If we just dive into running a test, we may miss some very important things about our data that would tell us that we need to use something else. We're also going to use plotting to understand assumptions and run diagnostics on the tests that we have done. So we're going to plot before we do stuff and after we do stuff. And then sometimes we use plotting to discover new relationships. We use it to explore the data to understand how things go together. So we're going to use it throughout the process, but we always want to start with plotting. We want to understand our data well before we start running any tests. Now, one thing about data visualization is there's this visualization paradox. What's interesting is it's often the most informative aspect of our analysis, and it often communicates the data story the absolute best. So when you're writing a paper, usually the figures that you put in are going to be some of the most influential and informative part of your paper. However, it's also the most abused area of quantitative science because figures can be very, very misleading. So for example, if you just look at this right here on the side, we have Democrats, Republicans, and Independents. And if you look at this plot, your first impression is Democrats are like 10 times higher than Republicans and Independents. But it turns out they're starting at 53 and going up to 63. So they're only showing a 10-point scale, even though it really should be like a 62-point scale. What this does is it immediately gives a false impression. Even though the numbers are actually correct, because they took away the baseline, which is really important for a bar graph, it can give the wrong impression. Now, if you have extra time on your hands, I recommend going to this link, Misleading Graphs. It has a bunch of ways that graphs are made to be misleading, and sometimes it's on purpose. Sometimes it's just ignorance by the individual making it. But it's good to go look at all the different ways that are really common, how people end up making really misleading graphs. Now this is the same data, but this time you're actually showing the baseline. So you have the 0 at the bottom, and it goes all the way up to 100, which is important here because that is the full scale of what could be shown. And when you look at this, suddenly it doesn't look wildly different. There's still a difference, and that's important. The Democrats here are a little bit higher. But that, in and of itself, is not a huge difference, and that's really important to also portray. What's also really interesting, if you look at this graph, is it mentions a margin of error is plus or minus 7%. And you'll notice this graph does not highlight any uncertainty. Instead, it just looks like those are solid values that represent the reality of life. What we're going to show in our data visualizations is we want to highlight the error, the uncertainty in the data, the movement that happens. And we're going to understand these terms a little bit better as we get into chapters 3 and 4 when we talk about the mean, median, and mode, and then variance and range. But the important thing is that we represent the data as they are, not as just a simple summary that doesn't have any other alternative explanations. So how do we build a good data viz? So it's important that your graphical method, the type of plot that you choose, it should match the level of measurement. So we've talked about this before. Measurement, it's going to determine the types of analyses we can do even with graphs. This is going to become more clear as we give more examples. But the idea behind it is we want to know what our measurement level is for our variable, and then we can pick what type of plot we want to use. We also want to label all axes and include a figure caption. We want to make it very clear what everything stands for in the plot. It's also really important to have simplicity and clarity. It's going to be tempting to throw as much stuff in there as you can to just have everything in one plot. But one thing that's really clear after years of doing this myself is anything that's even remotely complex is going to confuse a reader really fast. What you want to be able to do is have the reader understand it quickly and with little effort. That way they're going to understand the message without feeling like things are being hidden or things aren't clear. Now, one way to do this is we want to really avoid chart junk. That's a term that's been thrown out there by a number of data viz experts. These are things that your data visualization just doesn't need in it. These are like pictures instead of just points, or we're using a different size cartoon instead of just a bar graph. Those things, although they make something maybe a little bit more interesting at first, can start to paint very different pictures of what the data is actually saying. Now, unless there are 3 or more variables, avoid 3D figures. And even then, I would recommend avoiding it. There are ways to deal with 3 or more variables and how they relate to each other without going to 3D figures. 3D is just super hard to understand, especially on paper. And a lot of our output as researchers is actually either electronically on paper or actually on paper. And when that happens, a 3D figure can get really difficult to understand. Now, black and white and grayscale / pattern are fine for most simple figures. We're going to use color when possible here, as a lot of journals have gone online and they'll show the online color version. But what's important is that the color isn't absolutely essential for your figure unless you're willing to pay for that so that's in print. So what I end up doing is I use color, but I make it in such a way that if someone were to print it out in black and white, they would still be able to understand the message. With data visualizations, this is not something that there's just a hard and fast rule for everything. It takes a lot of practice. And honestly, when I'm building a data visualization, it starts from scratch. The first editions are not very good, and it just builds up until it's something that's really beautiful. Now, the effort that you put into a single data visualization is going to depend on what you're using it for. If you're just exploring the data and trying to understand the data, then you don't need to make it super elaborate and really pretty. You just need it to work. Now, if it's going to be something for a publication, that's going to be something that you want to spend a little bit more time on, do a little bit more exploration of some other types of ways to represent the data and see what communicates it best. Some resources to understand how to make a really good visualization. There's a guy, Edward Tufte. He has some really nice guidelines. He has several books about data visualization. He is pretty extreme in some ways, but he can give you some pretty good pointers on how to create a good graph. R for data science, it has a ton of great stuff in there, specifically how to do stuff in R, but there are a bunch of pointers on how to make really good R graphs. And then data visualization for social science by Healy is really a good one to understand data visualization as a whole. It's very thorough. It helps you understand how people understand data visualizations from a cognitive perspective. It's definitely worth your time if you're interested in understanding more about data visualizations. So one of the first things that we try to understand with a lot of types of data, particularly ordinal and nominal, is frequency distributions. And this is simply just counting the number of occurrences of each event. So you can use it with continuous. You see it a lot more with the ordinal or nominal variables. You can use a table F or table 1 function in the furniture package in R. This output right here in this table that you see, this is from table F, and you get the variable name, the possible levels, and missing values, the frequency of those. So you got 216 of 1, 260 of 2, etc., and then there's 24 missing, the cumulative frequency, the percent, etc. What's nice about this is you can start to see central tendency. If it's continuous data, we can see where the center is, which we're going to talk about more in the next chapter, or the most common value with categorical data. That's often a very important question, is what's the most common response here? And in this data, we can see pretty quickly that it's 2, but 3 and 4 are very close to it. So there's not a high proportion that just picked 2. Really, it's only 26%. So they're roughly equal in this distribution. What's also nice, and one reason why I recommend using frequency distribution, is you can see the range and extremes. So really quickly, we can see there's just values 1 through 4, and there's some missing. Sometimes when you're working with data, maybe someone miscoded something, or there's a surprise value in there that maybe was from a survey that you downloaded from the CDC. And it could be like -99. And so that would pop up in the frequency distribution, and you would see that really quickly and know, oh, that doesn't look right. There shouldn't be a -99 here. That is something you want to catch way before you're starting to run any statistical tests, or even taking a mean or median or mode or anything like that. So going right into making a figure or frequency distributions, and we're going to talk about in a moment combining those, it really quickly can tell us a lot about our data. So like I said, we're going to combine frequencies and data vises together in this perfect union, and that's why there's a heart there. So a bar graph is essentially a frequency distribution in a visualization form. So what's nice about using a bar graph instead of just a table is, as the levels get more and more, it's easier and easier to spot patterns. So in this case, we have this variable called x, and it has 4 levels. Really quickly, just by looking at this figure, I can know that level 4 is the lowest of all of them, really fast. Didn't take really hardly any thinking on my part to understand that. I also know pretty quickly that level 1 and 3 are roughly the most, and level 2 is pretty close to those as well. We also have what are called histograms. Now, a bar graph and a histogram are often mistaken for being the same thing. What's important is that a bar graph is representative of discrete values. Discrete meaning there's just one value and there's no blending to the next value. So it's like ordinal or nominal data, where level 1 is discretely different than level 2. And level 2 is discretely different than level 3. Now with truly continuous data, where you can have a value of 0 or 0.1 or 0.001, the way that we represent those is with a histogram. And you can know that it's a histogram versus a bar plot by looking at if the bars are touching. So a histogram often can look just like a mountain. It's all the bars are connected to each other, and so they're all kind of formed to one. That's going to be a histogram. Now sometimes the bars will be, they'll have lines between them so you can see the difference between the bars a little easier, but they'll still be touching. A bar graph, they're not going to be touching. And what's important about that is that it portrays the type of data that you're working with. If you have a bar graph and they're not touching, that suggests that they are discrete units. With a histogram, with them touching, that means they're continuous. They can flow from all the values in between. When it comes to histograms and bar graphs, these are often the two first line of defense to understand your data. You bring your data in, this is some of the first stuff you'll want to use to understand how things are looking in your data. I recommend using these just really quickly. They don't have to be beautiful. You just want to use them to understand the distribution of your data. Now I keep using that word. I keep saying distribution. And what it means is just the way that the data points are scattered, how things are. So when we say a distribution, it's just where are the things? Where are the values? So for continuous, we're often going to be talking about a general shape of the distribution. We're going to talk a lot about normality in this class. And if you look at this histogram here, this is roughly normal, where it's this kind of bell-shaped curve, and we're going to define that a lot more later on. But that's a shape of that distribution. We're going to also want to look at exceptions or outliers, things that are crazy points, points that don't make a ton of sense, or points that just are really far away from the other points. We're also going to look at modes where the peaks are. We're going to look at center and spread, which we talked about in chapter 3. And again, a histogram is a really good way of displaying that. For categorical, we're going to look at counts of each. So generally it's not going to be a general shape, but instead we're going to talk about the counts of each level. You'll also want to use things like percent or rate. So those can be really useful to understand where values are really high or really low. We'll want to use a bar chart often for this, and we just recommend avoiding a pie chart, as in a lot of cases they can get really confusing. There are times where a pie chart is quite useful, but especially as the levels get higher and higher, it's harder and harder to understand what a pie chart is telling us. Some cognitive science has shown that a bar chart is far more easier to understand for a reader and quicker for them to understand. So let's apply this to our friendly ENO data set. So we're going to walk through an example in R showing how to get all these things. Hopefully you can use this as a guide when you're working with any data for the homework or your own data. So as a reminder, the data, this is how they look. The variables we're going to use are the major. So one is psychology, pre-med, etc. Whether they are a regular coffee drinker, if they have a phobia of the essentially numbers or math. And then math quiz, it's a score on math background quiz, which is just going to be a continuous variable. So we have major, which looks like categorical, coffee categorical, phobia is kind of an interval scale where it goes from 0 to 10. And then math quiz looks like a ratio scale. It's a score. So the first thing we're going to do is read in the data, and we're almost always going to be using these three packages. We'll use a few others. In my first lecture on R, we talked about how to download these. Reach out if you have questions about downloading these. This is something we'll talk about in class as well. When you download a package, again, it just comes to your computer. But every time you want to use it, you got to open up that package, and this is how we open them up using the library command. We'll also use this a lot, where we use the package name : and it's not something you have to do, but it's something we're going to do in this class to show you where each function is coming from. So import is coming from Rio, is what that is saying. So in this case, import, we're going to import this data set. And then, which is the pipe, it's just saying, and then we're going to rename all the variables to lowercase. So we just read in the data, renaming all of them to lowercase, and we're assigning it the name data raw. So now, whenever we want to access that data, we can go to data_raw. We can also clean it up a little bit. In this case, we're going to take our data, and then we're going to mutate. Mutate just changes or creates a new variable. In this case, we're creating a new variable called major F. And all it is it's the factored version of what was our major variable before. So major was just numbers 1 through 5. What we want to do now is turn that into a categorical variable. So we're telling R that it's a factor. It's a factor. And the levels are 1, 2, 3, 4, 5. And the labels for those are psych, pre-med, biology, sociology, and economics. And then we just close all that up. So right there, if we were just to run that, it would just create a new variable called major F for the factored version of major. And then we can do essentially the same thing again. So we pipe again, and then we do that for coffee. So we're just taking coffee, creating coffee F with the factored version of it. The levels are 0 and 1. And the labels are not a regular coffee drinker or regularly drinks coffee. And then at the end, we don't use a pipe because we're done. So we've done what we wanted to do with the data to clean it up. And then we save it as data clean in this case. And then we're done. So no pipe at the end because we're just done cleaning it up. Next step is to look at the frequency distributions. To do this, one way is to use the table F function from the furniture package. So we can pull from data clean, our cleaned data set, and then put that into table F and just tell it the variable we want to look at. In this case, major F is the variable. So major F, so one of those that we just cleaned and we gave labels to and told R that it was a categorical variable. And so major F is telling us that there's 29 psychology majors, there's 25 pre-med, 21 biology, etc. It also tells us that there's no missing, so we don't have any missing values for this variable in this data set. We also can do this with phobia, even though phobia is somewhat continuous. It's an interval scale where we have 0 to 10, and we can see where the majority of individuals are at. The majority are between 0 and 5, really. And then there's only a handful that have these really high phobias. For data vizzes in this class, we're going to use a package called ggplot2. This provides us with the most powerful, beautiful framework for data visualizations, and it has a vocabulary that you can learn. So ggplot2 is going to be important for us to start to understand. You don't have to be a pro at it. That's okay. You have me and other resources to ask questions and find out how to best use it. But it's the one that we're going to use here because it is the most complete, and generally it does the right stuff given the type of figure that you want. The way that it works is that it's built on making layers. So generally we're going to start with a blank canvas, and then we're going to add layers onto it. So you start with a blank canvas, and then it's like painting. So you're going to paint one of the geoms, which is just going to be one way that the data is represented. So geom bar does bar charts, or geom histogram does histograms. And it's like it's going to paint the histogram on there for us. And that's going to be another layer onto the ggplot. So let's try an example of using ggplot. So we're going to try a bar chart first. Now, like I mentioned before, what we start with is this blank slate. So what we're given it is the data. So we're starting with our data. And then we use a pipe. And we're given that to this ggplot function. What that's going to do is just start our canvas. And then whenever we're adding stuff to ggplot, we're going to use a plus. And so AES major F just tells it we want to use major F as a variable. Whenever you see AES, it stands for aesthetics. It's just controlling what variables we're using in that plot. So this one is just saying we want to use data clean. We want to get a blank canvas, and the variable we're going to use is major F. And so we get this blank canvas that just knows, oh, you want to use major F. I don't know what else you want to do, but this is what I'll start with. Now, if we add just one more layer, so we just do a plus and then geom bar, it throws bars on there. So it paints it on there for us. So now we can see psychology is the most common, followed by pre-med, biology, sociology, and then economics. We can do the same thing, but with a different variable. And so instead of major F, now we're doing coffee. So we have data clean, ggplot, AES coffee, and then geom bar. And now we have coffee 0 or coffee 1, and we can see for 0, there's roughly 50 something, high 50s. And for coffee 1, which is regular drinker, not a regular drinker, it's just a little bit above 40. After trying geom bar, to do a histogram, all we have to do is use geom histogram instead of geom bar. And in this case, we want to use a continuous variable, so we're going to use phobia. Everything else is the same. You'll notice we have the data. We have our blank canvas. Oops, sorry. Blank canvas. We have our AES. We're just telling it the phobia. And then we have geom histogram. But notice this histogram doesn't look amazing. For one thing, all the bars are not touching each other, which means something is not quite right with it. And what it turns out is if you can use the number of bins. So in this case, we're saying we want 8 bins. So that means we have 8 bars, 1, 2, 3, 4, 5, 6, 7, 8. So it splits all the data up into 8 parts. Or we can say bin width equals 5. So this is, each bar is 5 units wide. Or we can say bin width equals 4. So that's the width is saying it's 4 units wide. Now notice, depending on, so these are all phobia right here. This one, and this one. They're all pretty different. They're all telling us a slightly different thing about the data. And so whenever you're making a histogram, you want to play around with it until you really feel like it's representing the data well. For example, I think this one represents the data really well. There's not so many bins that there's gaps between the bars, but there's not so few bins that, like this one, it's all just kind of clumped together and you can't really see what the distribution is. Now we can do the same thing with math quiz. So this is another continuous variable we have here. And this one you can see has a little bit more of a symmetrical distribution to it. So the really low and high scores are less common than the middle scores. We also can do it by a factor. So what we can use is what's called a facet. Now, a lot of times we're trying to understand maybe how math quiz acts depending on some other variable. So what we can do is we can add one more layer. So we do a plus, and then facet grid. That just means we're going to facet them on a grid. And then the dot tilde, that's that funny little thing that's in the upper left-hand corner of your keyboard. And then the variable we want to facet by. What this is saying is that we want columns to be represented by coffee. If we put coffee here and a dot on this side, it would mean we want coffee to be rows instead of columns. So here what it's showing is not a regular coffee drinker. This is what math quiz looks like. Regularly drinks coffee. This is what it looks like. And just eyeballing it, it looks like not a regular coffee drinker is somewhat bimodal, and we'll talk about what that means in the next chapter. But you have a peak here and a peak here. Most of them are 30 or higher, roughly, but you have this group that's pretty low. And then the regularly drinks coffee. Most of them are right around here, but it's the majority are just kind of congregated right in the middle there. So this tells us a little bit about our data and how maybe the math quiz might be related to whether or not you're a regular coffee drinker. So like I mentioned, we can make it so coffee F is now represented by the rows. So when we had it here, it's columns. Here, it's rows. Now in a case like this, it can be really useful to use rows because we want to actually see where people are. And this one shows that if you're not a regular coffee drinker, you're either generally lower than a coffee drinker or higher. But you're rarely right at the same, or this peak here. So it's really interesting. You're either not doing very well, maybe you're just too tired, or you're getting enough sleep and you don't need coffee, and so you're up here. So the last thing we're going to talk about is another way to break up the data. So a histogram, like you were seeing, it's just chopping up this continuous data into pieces and then counting how many fall into those pieces. So here there's 2 that fall into this area between here and here. We can do this a different way with what are called deciles or quantiles. And so here what we're doing is we're taking our data set, we're pulling out just stat quiz, just that variable, and we're throwing it into this quantile function. And this quantile function is going to allow us to tell it what percentiles we want. And in this case, we want it at 10, 20, 30, etc. We want to find out what the values are at each of those points. So if we run this code, we get 10%, 20, all the way up to 90. And we get to see that at 10%, so if you go in the distribution to the lowest 10% of people, you're at 4. The lowest 20%, 6. And you can look all the way up to the highest 90% would be 8.1 on this stat quiz variable. Now note, it's going to give you an error when you have issues with missing values. So in math quiz, we have some missingness. The way to deal with that is just adding this na.rm equals true. Now note, anytime you're doing like a mean or a quantile or median or any statistic, R naturally has na.rm equals false. Now this says remove NAs. That's what this argument is saying. So when it's true, it's going to remove the NAs and just look at what is actually there without the NAs in it. But by default, R leaves the NAs in. And that can be annoying sometimes, but it's really important because it means you won't overlook missing values. So if you're running this, you would immediately know, oh, there's missing values in Math Quiz. I didn't realize that, and now I know. Then we can just use this na.rm equals true, and that solves the issue. We can now see what is actually there, and we know that there's missing data there. We also can get quartiles, which is just breaking it up into 4 chunks at 0, 25, 50, 75, 1. The 50 is usually the median. So you can think of that as a median. This is the min. This is the max. So the min is 1 in this data set in Stat Quiz. The median is 7. We'll talk about that more. And then the max is 10. We also can just pick any percentiles, any random ones that you want, and you can get the value at that percentile. So if you have any questions, please post them to the discussion board. We'll be able to discuss those in class and go over any of the art questions that you have. Notably, the most important stuff in this lecture is understanding why we use figures and ways that figures inform us and what types we can use. We're going to introduce other figures in the next couple of lectures, but notably our starting point are these really core ones, these frequency ones with bar graphs and histograms. The next chapter is going to be about center and spread, so we're going to talk about mean, median, and mode, and then we're going to talk about how a distribution is spread, especially across continuous variables. So we have range and variability and standard deviation that we'll talk about next.